Hello everyone. In this video, we'll discuss a vision of computer architecture research over the next 15 years. Computer architecture is at turning point. The approach that worked for decades are reaching their limits and future computer systems will look very different from what we use today. Coming up in this video, we'll look at why traditional architectures are no longer enough and explore what's coming next, including heterogeneous computing, energy efficient design, memory centric architectures, AI driven hardware, and new computing paradigms. So, why does this topic matter? For a long time, performance improvements came almost automatic. Faster processor arrived every few years and software simply became faster without major changes. But today, the situation has changed. We are facing power limits, thermal constraints, and increasing system complexity. At the same time, applications like artificial intelligence, data analytics, and cloud computing are growing rapidly and demanding for more hardware. Because of these challenges and demands, the next 15 years of computer architecture research will be extremely important in shaping the future of computing. To understand why another major change is needed, it helps to look at how we got here. Historically, Moore's law and Dennard scaling powered decades of progress. When clock speeds hit limits, we moved to multi-core processors, then GPUs and accelerators. This evolution shows why another architectural shift is now necessary. So far, we have seen how computer architecture evolved and why change is necessary. Now let's look at why traditional approaches are no longer sufficient. Today, the biggest challenges are no longer computation speed, but power consumption and data movement. In fact, accessing memory often consumes far more energy than performing arithmetic operations. Because of this, traditional performance scaling has become inefficient and unsustainable. This naturally leads to an important question: what challenges must future computer architecture research addresses? First, how do we improve performance without increasing power consumption? Second, how do we program increasingly complex systems efficiently? And then, how do we ensure security and reliability directly at the hardware level? These challenges shape the key research directions that we are going to discuss. One of the most significant trends addressing these challenges is the move toward heterogeneous computing. Instead of relying on a single general purpose CPU, future systems will combine CPUs, GPUs, and specialized accelerators designed for tasks such as AI, encryption, and data processing. Closely related to heterogeneity is the growing emphasis on energy efficient design. In the future, energy efficiency will be more important than raw performance. Techniques such as near threshold computing and approximate computing, where the perfect accuracy is not always required, will play a key role. This also means hardware and software will increasingly be designed to minimum energy consumption. Even with efficient processor, another major bottleneck remains memory access. To address this, future research will explore processing in memory and near memory computing, where computation is placed closer to where data resides. By reducing data movement, these architectures significantly lower latency and energy consumption, improving overall system efficiency. Another powerful force driven architectural change is artificial intelligence. Artificial intelligence is one of the strongest drivers of architectural innovation. Future architectures will support arithmetic, massive parallelism, and adaptive designs that evolve with AI models. In many cases, hardware and algorithms will be designed together. As architectures grow more complex, security becomes impossible to ignore. Recent hardware vulnerabilities have shown that security cannot be added later. It must be built in from the start. Future architectures will include hardware level security mechanism, secure isolation and trusted execution environment along with improved reliability. Improving existing system, researchers are also exploring entirely new computing paradigms. These include quantum computing, neuromorphic computing, and optical system. While this technology may not replace classical computers entirely, they will complement them for specific high impact applications. All these trends point to a broader shift in how research is conducted. Computer architecture research is moving away from isolated hardware design toward full stack code design involving hardware compilers, operating system, and applications. This shift makes interdisciplinary collaboration more important than ever. Taking all these directions together, the vision for the next 15 years become clear. Future architectures will be application driven, energy efficient, secure, and highly specialized, while still remaining programmable and scalable. Here comes the conclusion. To conclude, computer architecture is entering a new era driven by physical constraints, emerging applications, and innovations across the entire computing stack. Thank you for watching.